I recently completed the RTK accuracy video. I circulated among a few peers before we publish it. One of my peers said, you should teach folks how to do these tests of their RTK accuracy themselves. I'm somewhat loath to teach an error theory class because it would take a couple hours. Thinking about it, I thought, well, you know what I'll do is I will bring it into Excel and I'll show you, because Excel actually knows and does all the formulas, so I'm not teaching error theory. I'm just going to teach you how to test it in Excel, because you're not going to do this longhand anyway. Let's get started. The information that I referred to and the graphs that I referred to in the RTK accuracy video is shown here in front of us. What we have is nearly 3 hours of information collected at 1 second intervals. So I have a little over 10,200 samplings of northings, eastings, and elevations at 1 second. If you look at how the columns are set up on the slide, you'll see that we have 1 second on the left in the left-hand column. Then you have your northings, eastings, and elevations. In the top right-hand column here, you'll see that I have included the instrument specifications, which is 1 centimeter, which is 3/100ths, and 1 part per million. In this particular sample set, the part per million doesn't factor in because I was 70 feet away, and also rod bubbles, or the fact I wasn't trying to set up on a known value. So this is a pure measurement, which depending on the system that you use, it can be continuous topo or continuous measurements to get this information, or you could sit there and hit register 10,205 times. What I'm going to show you is that RMS is a 3-card Monte. It doesn't report what you think it's reporting, and I'm going to demonstrate that before we actually break down the data. What root mean squared does is it's easier to demonstrate than it is to explain it, but what it's doing is it's averaging shots as it goes, and that's why it's inaccurate, because as you see in the accuracy video, that your northings and eastings are constantly moving, or as shown in the graph. They're never quite the same. And so when you have a shot and you start falling out a tenth, it's not going to show up in your root mean squared. Let me show you why. First thing we have to do is clarify a few terms. Sometimes they're interchangeable and sometimes they're not. In this case, we're using the mean of a data set, and that is the same as the average. And we're going to calculate the standard deviation, which is also the same as the standard error. So let's get started. I'll show you how root mean squared works and why it's not an indicator of anything useful to the land surveyor. I'm going to mean the first 10 measurements. In Excel, I start out with an equal sign anytime I use a formula. Average, parenthesis, and I grab these shots and I go down to the first 10 shots. In this case, in my eastings, I have an average of 0.94 through the first 10 shots. And if you look at the shots shown here, you have a 9.4, 9.5, 9.4, 9.3, 9.4. And so what my root mean squared would show is it'd be showing that 1/100th. My root mean squared would be within 100th, 100th and a half. So let's just say that at this point on the 11th shot, let's say I was 1 foot off of the previous 9 measurements. We'll make this a 5. Look at this. When you look at my root mean squared, it only moved at 1/10. So what would happen is I just moved a foot. If I hit register, I'm a full foot different, and it only changed my root mean squared by 1/10. Why? Because that 1 foot measurement is 1/10 of the 10 measurements taken. So it's not telling me that I just moved a foot. It's saying that I'm within 1/10 of my previous shots if I was watching my root mean squared. And we know that RTK doesn't have a foot error in it. It has approximately 1/10. So if I just moved 1/10, I just moved 100th. So on the root mean squared. So if this RTK unit is changing position, it would take a longer time than one single measurement. But if it was moving over the course of 1/10, it would never show up in my root mean squared. over the course of 2/10, it wouldn't show up because of the gradual way that it goes over. And that's demonstrated here. So when you see root mean squared and it's within 100th or 200th or 300th, it really doesn't mean anything, especially the longer you're there. And as this easting in this instance falls or gains through a tenth, you'll never see a difference in your root mean squared. Your answers are quite different. Your true answer is quite different. So that's just something to know, that root mean squared is bunk. It really doesn't mean anything from a surveyor's quality control perspective. Okay, next we're going to go ahead and mean the 10,205 measurements that I have in my Excel spreadsheet. We'll start with the northing because, as I said before, northings and eastings are not correlated. So we start here in the northing, equals average, parenthesis. Now this is kind of a trick. When you have 10,000 lines of data, you don't want to sit there with the down arrow all day and run through it. So the key is to go shift and down arrow, and that will highlight everything through the all 3 hours of data. And I hit return, takes me back up here, and there is my average northing. And to just show you the formula one more time, it's equals average, parenthesis, get the first one, shift, and down arrow. And you have to do this in a rather fluid motion, otherwise you're not going to get what you want. And so I'm going to continue, and I do that again for the elevation. Okay, so now that I have the average, that's the most likely answer of the position, the most likely location of the position measured. And so next, I want to know the standard deviation. And the standard deviation is the difference between the average and the measurement, which is called a residual. So if I had an average of 5 and I measured 6, I would have a residual of +1. So the standard deviation actually takes in all the residuals, and then there's a formula, and it's the sum of the square root divided by the number of measurements. You don't need to know that because Excel knows it for you. Of course, we start out with an equals, as we do with all formulas, and we start by typing in ST, and it'll show up, and it's the one that you will use is stdev.s. You could use .p, but we're going to use a set of data, and we'll use the s. Then it's asking me for the columns. I could select them the way I showed you earlier, but I also know that these columns are B2 through B205, 10,205, and let's see what we get. Now, we end up with 0.03 hundredths of a foot. Let's do the deviation for the easting. So we go equals ST, there it is. We double click on it. We say this is column C2 through 10205, C10205, parenthesis. Now, you notice that we're within 300ths by 300ths 68% of the time. That's your standard deviation. That's the instrument specification. If that number looks familiar, look here. And what that means is your standard deviation is at the instrument specification. Deadly. Let's go ahead and do it for the elevation and see what happens there. Equals STD D through D10205, parenthesis. Well, look at that. In this particular selection set, we don't make our instrument specifications. They should be at 600ths. Well, maybe we don't have a big enough selection set because they don't tell you in the specifications what that specification, how they determined it for Trimble or for Leica. So obviously our selection set isn't big enough to get the mean to determine the standard deviation within the specification. It's not too concerning. It's 0.03 worse than the spec. The thing is you very seldom will ever be better than the spec because the manufacturers have a vested interest in advertising accurately the most accuracy they can. Why is it you think they report standard deviation as opposed to 95%? The reason is 95% puts them at 6/700ths. Standard deviation puts them at 3. If you don't know the difference between these terms, you could run around thinking you're within 0.03. I don't want to hunt and pick through 10,000 different measurements here, but I want to know what my min and my max are in the range. So Excel will do that for me also. Equals large, and again, the same selection set, B2 through B10,205. Now this is the trick, comma, 1, meaning I want the highest. So there is my maximum measurement in the northing. I'll continue on through the easting and the elevations. Next, I'm going to calculate the minimum, the smallest measurement that I have in a series. I type in equals small, I put in my series, B2 through B10,205, comma, 1. I want the smallest measurement. I'll do that again. Now I'll do it for the eastings. I type in equals small, parenthesis, C2 through C10,205, comma, 1, small, and I'll continue on and finish these out. So I've completed my minimums and my maximums within the series. And in doing so, let's see what we have. Right here, you'll see that my maximum northing is shown as a 0.65. My minimum northing shown is a 0.37. So right there I have almost 0.3 between my min and my max, or 0.25. Let's look at the easting. 94 and a 72. There's 0.22 between my minimum and my maximum in a 3-hour measurement period. Let's look at the elevations. I have a 1.2 and I have a 40 point, almost 50. So in this series here, I have almost 0.7 between my minims and my max on my elevations. And that is the story of RTK. In my last video, I talked about folks that waste time taking more than one measurement or taking a series of measurements over a short period of time. With the idea, I think the logic is that it's like wrapping angles. The more you do, the better it is. But it technically doesn't work that way. And you can see that here in the data that we're looking at. And I showed it before. But let's just take any random 3 minutes of data, which 3 minutes is 180 seconds. So for the first one, I'll go from 1 second to 180, and I'll get the average for that period, which is the mean. So I go equals average B2 through B180. Actually, technically it's 181. Okay, you'll see here that my average in my northing is a 0.55, and my overall average of 10,000 shots is actually a 0.49. So there's 0.06. So I'm 0.06 off of a 3-minute average from a 3-hour average. Let's do the same for the easting. Okay, now I've completed the averages over the first 3 minutes of my measurements, and as you can see here, I have a 0.94 in the first 3 minutes, and my average over 3 hours is a 0.88. So there I have 0.06. So I basically have 0.06 in the first 3 minutes, 0.06 in the northing, 0.06 in the easting, and in the elevation, I actually have 1/16 in that first 3 minutes from the average or true elevation. Briefly going back, I show you what the average data is over 180 seconds, which is 3 minutes. And if you just look over at the 25th shot here and you look at the difference here, I have a 55 and I have a 59. That's within 400ths. I have a 44.94 and I have a 44.94. I have a 340.62. I have a 340.58. This is just one random shot. So if you look at these various shots over here, you'll see they do not vary that much from the 3-minute average or just a single shot. And that's why you're generally wasting time to sit there and collect 3 minutes of data, because you're not going to see the variation in 3 minutes as this thing's falling. And as I described earlier, it's not going to show up in your root mean squared. Everything looks hunky-dory. However, any single one of these shots in that 180 seconds is essentially equal to any other shot and will be close to the average. So you're wasting time. Okay, so now I'm going to show you what 5 minutes of data looks like. Now, 5 minutes is the outer limits of an RTK collection waste of time, because now you're getting close to where you just should be doing static. So I type in the formula, average, and I'm going to take 300 seconds, which is 5 minutes. And I'm going to just take 500 to 800. Okay, to look at where we are in those shots is, you'll see in my northing, I'm within almost 400ths of the 10,000 shots. Let's go ahead and do the same for the eastings. Okay, so I just completed a random sampling of 5 minutes of data, and that sampling ends up within about 3/400ths in the northing. We end up within 3/400ths in the easting, and I'm averaging 700ths in the elevation. It doesn't really matter. It's a 5 minute sampling in the middle of it's an hour and a half into it. And if you went in and you took other samples, you would see this thing all over the place. And of course, you would have some of those extremes that we saw in there. And that's the random deal, is we're within our standard 95% of the time. However, 5% of these measurements fall way outside of the standard deviation, as you can see in our mins and our maxes. And that's why RTK is appropriate for some things, but it's certainly not appropriate for others. You have golf ball accuracy in the horizontal. This should show you what a good sampling of data of how to calculate your own and run your own test. Regardless of the equipment manufacturer that you have, you're able to run your own test using Excel. Load in all of your coordinates on 1 second epochs, 1 second measurements, do an average, do a standard deviation, take sample sets, and check the data. And what you'll find, obviously, is you're within the equipment manufacturer specifications. You're within 600ths in the northing, 600ths in the easting 95% of the time, and 1200ths in the elevation 95% of the time. Now understand that that's 600ths plus, 600ths minus. So you have a 1200ths northing ellipse and a 1200ths easting ellipse being plus or minus on that, and you have your elevations. So if golf ball accuracy is okay, then you should be using RTK for horizontal. If variations up to 2 or 3 tenths is okay, then you can use it for your vertical, because those are 5% of the shots. So if you take 100 shots, 5% of them are on the outer limits, and they're not necessarily within 2 or 300ths. Okay, the last thing I'm going to show you today is how to graph the data. I'm going to graph it by time and northing. This is where I do my shift and down arrow to get all of my data. I go up here and I say insert, and under insert I have this scatter shown here. When I go in, I check scatter. Now you can't use any of the curved ones because our data set is relatively small and close together. So I recommend that you use the scatter with straight lines shown here. And there's my plot. And you can see at this particular scale that these are 28 minutes, 57 minutes, so on and so forth. To change my scale, I move this plot over, and you'll see here that at this scale, I have my every 3 minutes or so is the timeline here, shown out to 2 hours, 47 minutes. And when you come up here and you look, you see my variations in my northing through here. And as you recall, my mean was right here at 45 was the mean on this. So you can see how graphing how the RTK measurements look over the course of 3 hours. And I'm going to scale it, zoom out a little bit here so you can see this a little better. There you go. I'll move it over. Okay, so these are my measurements. Now this is real data. So if I were to stop on a point, it'll show me what my northing is at this point at 59 minutes and 37 seconds into this. If I come up here to this top point up here and get the data, it'll show me that at 1 hour, 20 minutes, I was at a 0.58. If I come back down here and I look at the bottom of this one, 11 minutes later, I'm at a 0.38. So I have 2/10 in 11 minutes. So imagine if you're staking. You set a point, building corner. 11 minutes later, you're doing a 5x5. 11 minutes later, you're setting the next one. Right there, it shows that you have 2/10 in your northing alone within 11 minutes. So that's at a 131. Let's come up here and grab some of this data. At 141, 10 minutes later, I'm up to 54. So now I'm about 15 hundredths different in 11 minutes. And you'll find that throughout the day. Now if I come in here and I grab a point in the middle, well, it's easier to grab the ends. So I come in here at 145 and I'm at 47. So I'm almost at the average for the day. You can do this for your eastings and your elevations. I'll just run through the chart. Select the data. I'll do eastings in this case. I do shift and down arrow. I have my eastings. I go to insert. I use the scatter chart shown right under view here. Bring that down and I grab my scatter with straight lines. And there are my eastings. Now you can see that I'm at a much different scale here, so I would have to adjust my scale. When I zoom in and I'm looking at this particular chart, you can see that it needs to be adjusted by scale. So how do I do that? I come in here, I select the chart, I have a chart design here, which can tell me, offers me various formats, or I can go to format, and over here I want to change the size to 12 inch by 12 inch. And I scale that up. And when I scale it up, and then I scale back out, and you can see here that at 12 inch by 12 inch, it's adjusting my scale, and I'm able to check the data and look at it. And just to give you an example of the scale we're looking at here, it's actually in seconds, 4,803 seconds. And so that's about an hour and a half in. And if I come down here and I'm 5,000, it's 1,000 seconds. It's not really realistic. That's actually a pretty long period of time. But you get the understanding that you adjust this scale and you can go in. But frankly, you don't need to see this. This is just to give you a sense of how RTK measures. You're not going to use this graph really much more than that, just to get a sense of it's not a flat line. And if you were to overlay the northing onto the easting, you'll realize that they're not exactly correlated. As my northings go up, my eastings aren't necessarily going with them. They could be coming down. And what that creates is a larger delta XY. So if I'm +6 on my northing, but I'm -6 on my easting, and then the next shot's +6 on my easting and -6, it creates that issue, or it creates that, it makes them so that they're not relative to each other. Anyway, I hope this gives you a better understanding of how the RTK calculations work and gives you the background to run your own test. Literally can recreate what I did here in about 10 minutes with a data set. Thank you and have a nice day.